Welcome to my presentation about finding anomalies in Scratch assignments. Scratch is a block-based programming language commonly used to introduce novices to the concepts of programming. We use anomaly detection to help teachers with debugging their students' code and giving feedback. So let's dive right into it. Imagine a small task. Move a sprite whenever the space key is pressed. This script here is a correct solution for that task. It uses the move steps block whenever the space key is pressed. This other script is obviously wrong, because if you take a closer look, it's using the go to position block instead of the move steps block. Therefore, the sprite will result in the same position over and over again instead of continuously moving forward. For us, it's quite easy and intuitive to find the problem here. But in a classroom scenario where teachers are probably not highly trained in software development, the activity of debugging is much more complex than just looking at one script. Teachers have to help many children solving the same programming task at once. This is where automated tools can help. Especially, this is where anomaly detection can help. When you analyze all of the student solutions, you have a high chance to see many solutions that are at least partially correct and have that correct parts in common. The buggy script then is a rare deviation from the common behavior, and the idea of anomaly detection is to learn patterns that correspond to correct behavior and find the violations that likely are wrong behavior then. But how do we come from Scratch projects to patterns and violations? We need a representation of scripts that allows us to mine patterns. For this, we define script models. Script models summarize the control flow of the individual scripts and are labeled with instructions. From these script models, we extract pairs of blocks where one block can precede the other in program execution. These pairs of blocks are called temporal properties. We extract a graph summarizing these temporal properties, which depict block patterns. So now we have an idea how to extract common behaviors from Scratch programs. But how do we do that for violations? What we do is we compare block patterns that occur frequently with the temporal properties of every script. And if there are rare deviations, we mark them. The temporal properties of the buggy script do not contain the move steps block. If in our dataset of solutions for this task there are many correct scripts, we will find the pattern representing the correct solution frequently. Comparing these temporal properties, so the temporal properties of the buggy script, with the temporal properties of the pattern will result in a violation which directly hints at the missing block in this case. Our implementation can be configured to only report violations that reach certain parameter thresholds, and these reported violations are then called anomalies. We evaluated our approach on student solutions, and our evaluation dataset consists of student solutions for 6 different programs. 5 of them are tightly specified with a clear objective and varying complexity and size. The one remaining task was an open task where students were free to implement whatever they wanted to. The solutions were created by children aged 8 to 13 in programming sessions conducted by qualified teachers. We mined anomalies just like a teacher would, and that means anomalies separately for every of those projects, like tasks. And the good thing is that there is no manual work necessary, no writing of tests, no manual inspection of all programs, no need for a specification or anything. These are the numbers we found. So what you see now is the number of solutions handed in by the students and the number of anomalies that we mined. And if you take a closer look at the data presented here, you will quickly realize that based only on the number of solutions, you cannot predict how many anomalies are found. For example, if you compare the results for the elephant and the fruit, you will see that although the elephant task has a lot more solutions, there are only 10 anomalies reported. For the fruit task, which has a significantly smaller dataset, we found 460 anomalies. So you see that there has to be some other reason for how many anomalies are reported. And we conducted a sensitivity analysis about how the parameters you can configure for anomaly detection influence how many anomalies are reported, and you can read all about that in our paper. In addition to the quantitative analysis, we also conducted a qualitative analysis of our results because we wanted to know how useful are these anomalies and which categories of them are there. So we manually inspected the top 10 of all the anomalies reported for every task, so in total 60 anomalies, and we classified them into 5 categories. So the first 3 categories are categories that hint at defective code, so the anomaly, for example, hints at a bug pattern in the code or at a missing block or blocks in the wrong order. Then we have another category where the anomalies hint at unnecessary blocks that don't actually are a bug but still smelly. And then we have one category where the anomaly hints at distinguished work, for example, where students creatively extended the programs further beyond what the task required of them. In general, we found that the majority of all the top 10 classified anomalies hint at defective code. So for example, if you look at the results for the monkey task, you will see that 9 of the 10 anomalies actually hint at defective code. And that pattern repeats for basically every one of those 6 tasks, except for the open task. But there it's expected that there are some more non-defective anomalies because the programs are much less similar than in the other tasks. Overall, we found 46 defective, 4 smelly, and 10 non-defective anomalies. Now let's have a look at concrete examples from our dataset. This script is an example for the right blocks assembled in the wrong order. The cat should be programmed to say, "I got you," only after touching the ball. A common generic linter would not be able to identify this bug, as using a say block before an if-then block is not a generic bug pattern. In contrast to that, the anomaly reports this project-specific bug. The red dotted transition indicates that the say for seconds block usually comes after the if-then block. That's useful for the student. The student can fix the code, and the teacher can talk about script flow in class based on this anomaly. Another category of anomalies is the missing block category. Anomalies of this category hint at missing blocks in a script, such as the missing move steps in our first example. This script stems from the horse task, where the horse has to change color regularly. The solution of this student does not use the correct block. Again, this is a project-specific bug a generic linter would not be able to report, as the script at hand does not have any notable generic flaw. The reported anomaly, however, shows exactly this bug, the missing changed color block. Reported violations such as these are valuable feedback for teachers and students. The student can fix the code, and the teacher can explain when the task is considered solved. So overall, we identified the need to support teachers with tools for automated debugging. We came up with the idea to learn correct block patterns and inspect rare deviations from these coding patterns in order to find bugs. We found that anomaly detection in Scratch works and helps us find bugs, code smells, and distinguished student work. Particularly, we found generic as well as project-specific bugs, such as the wrong order of blocks or missing blocks. To sum up, anomalies provide valuable automated feedback to teachers and students without needing a specification test suite or any manual inspection.
Good evening. We are going to start the QA part of our first paper in this session. We have here Nina and Gordon to discuss all the questions and issues that you want to raise. So we already have one question by Max. He said this is nice work. How were the task description specified for the students? Is there merit in providing a pattern specification of expected solution given by the teachers?
Do you mean pattern specification to give to the learners or to improve the tool?
I understand that is the information given to the students.
So the information the students were given is just a textual description of what they're supposed to be doing. They did not receive information about the expected control flow or anything like that. It was just build a game that does this.
Okay.
I suppose some sort of pattern specification could improve the way the tool works and is able to distinguish between good and bad anomalies, for example. So I could imagine there's applications of this to improve the whole thing.
Mm-hmm. He said, like in giving pattern specifications so that they need not be learned, for example, for tests.
Yeah, so I suppose that's what I meant, right? It's an anomaly is just an outlier. It can be good, it can be bad. We don't know, but if you have some sort of specification that tells you what is good and what is bad, then that could possibly improve the application here. But the whole point of doing the anomaly detection is to provide teachers with a tool that does not require them to create a specification in the first place. And so we're trying to sidestep the problem of formalizing the expected behavior. But there could be synergies, surely.
Okay, good. So while more questions arrive, I have a couple of questions. One, if we are assuming that the right solution will be the most common solution. So what happens if this is not the case? It could be possible.
Of course, it's easiest if there's like one solution that is clear, that is the only path students can take, and the more solutions there are and possible solution paths, potentially, of course, the quality of the anomalies will suffer. But if there are is a sufficient amount of students who take similar approaches, it will still work because our patterns are on some sort of abstraction level that doesn't directly map back to only one script, but to a set of scripts that could possibly be a solution.
So I don't think the approach can replace an autograder completely. Right? If everyone does it wrong, then the anomaly will be the student who does it right. Right? So the anomaly detection only tells us interesting or special cases that deviate from what everyone else does. Now, in our experiments, it seems that in the majority of cases, the deviation seems to be wrong behavior. But we also had cases where the deviation is simply a student doing something in addition to what was requested, for example. But I think that's also interesting for a teacher to know.
Sure. Yes. Okay. We have here more questions. For example, Shane says, is the tool used after class, for example, during marking, or it is used during the class time?
Okay, so basically we can imagine both. Usually the teachers we talk to, they said, okay, usually we have a class for more than one session. So what we could imagine to do is let the students implement 4 sessions, get their programs, then analyze them, and then give them feedback at the start of the next session. But also you could try to use it for summative assessment at the end. But you have to be aware that this approach will not be 100% correct, like a test suite or something. So you have to take it with a grain of salt, and you cannot, as Gordon said, use it as an autograder at this point. But you could use it to improve the way you teach, of course, or to get fast feedback about all the solutions you got from the students and about the patterns that they used and so on. So that's an interesting aspect, that you can get feedback on a data set of solutions without actually having to look at all of them.
Okay, good. There is another question by Jose Miguel. Does the approach take a model solution or solutions as input?
So currently it does not. But in principle, a model solution could provide hints on what are good and what are bad patterns and which anomalies are positive or negative anomalies. So that is certainly one of the things we would like to look at in the future.
Okay.
Right now you can include them in the data set and they will slightly influence the patterns you extract, but it's not explicitly included in the workflow.
Okay. Okay, another question by Pedro. Did you analyze afterwards whether the patterns were overlooking some buggy solutions in the students' solutions?
Shall I? Well, there's at least one plot in the paper where we describe exactly that. So we looked at, in the evaluation, we have 6 data sets of student solutions where all the students did a similar implementation. And for 4 of them, we have, because they're simple enough, we have a classification into right or wrong. And we compared how many of the implementations that are wrong also have anomalies. And so I don't know the numbers off the top of my head, but the anomaly approach cannot detect all the buggy solutions. But I mean, that ties back to what we said earlier. It's not supposed to be a replacement for an autograder. It's supposed to inform the teacher about what's happening, what are special cases.
Okay. Let me check the time. Okay, we have still some minutes. Okay, I have another question. Do you think that this approach of detecting anomalies and common behavior could be applicable for other programming languages?
So the general approach to detect anomalies originates from other programming languages. In particular, we adapted a tool that was implemented for the Java language.
Okay.
So the twist we applied on it was the application scenario. The traditional software engineering anomaly detection approaches, you have a large corpus of data, which is one project you're working on, and you're using the same API at different places. And you're trying to identify anomalies in how you use the same APIs over and over. So we changed the use case in that we have repeated implementations of the same task and try to find anomalies there. Now, there's no reason this wouldn't generalize to any other programming language. So there's our tool, our implementation is specific to Scratch, but the idea of doing anomaly detection on student solutions generalizes to any language.
Okay, cool. We have some time, 1 minute and a half. If there is any other question or comment. I also had a comment about the threshold. I mean, how do you, is there any threshold or any quantitative measure that you use to identify when behavior is a common behavior?
Yeah, we basically have 4 parameters you can specify. The most interesting one for that question is called confidence. So that is the ratio of scripts that support a pattern, so that adhere to a pattern, compared to the scripts that violate it in that specific way. And the fewer scripts violate a pattern in that very specific way, the more confident we are in it being a true anomaly. So one that actually reveals a bug. And we did not take a look into how those parameters we can configure change the quality of the anomalies, but we conducted a sensitivity analysis concerning how many anomalies are reported if you change the parameters. We reported on that in the paper, but we definitely want to have a look at the change in quality if we change those parameters.
Okay, great. So thank you very much. Just on time, thank you for the authors and thank you for the audience for